Okay, we're going to look at theoretical yield, actual yield calculations. Well, let's do some simple ones first. Let's say each time you make cookies, you get a 90% yield. And so let's say baking cookies, 90% is your typical yield. So let's say what you're going to do is you're going to bake 100 cookies. So you're going to have a theoretical yield, Ty, of 100 cookies. But your actual yield is going to be what? If you have a 90% typical yield, then your actual yield is only going to be 90 cookies. So that's how we can do this. But let's say you actually needed 100 cookies. If you actually needed 100 cookies, but what if you actually needed 100 cookies? How many should you plan on making? Well, 110 is not going to give you enough. If you have 110 theoretical yield and you have a 90 over 100, 90 actual yield over 100 theoretical yield, how many cookies will that give you? So let's calculate it. So 110 times 90 divided by 100. You know, I'm going to come out one cookie short. I'm only going to get 99 cookies. So if I plan on baking 110, I'm only going to get 99 if I have a 90% yield. And so in order to get up, we have to use dimensional analysis. So what we're going to do is we're going to go with 100 cookies. This is going to be our actual yield. That's what we want. And therefore, to figure it out, for every 90 cookie, actually, what do I want to do? I want to do for every 90 cookies actual yield, I get 100 theoretical. Or in other words, for every 100 theoretical, I only get 90 actual. And so this is going to tell me, the actual cancels, this tells me in theory how many I have to make. And so 100 times 100 divided by 90. I better plan on making 111.11. In other words, I probably should make 112 cookies to compensate for that loss. Does that make sense? So 111 cookies I need to make. Yeah.
So you make 111, actually having 100 cookies.
If I want 100 cookies at the end, I better make 111 because I always lose 10%. And so 10% of 111 would be 11 cookies. Does that make sense? So that's how we would do this. This happens in chemistry too because, you know, you kind of get, you don't want to scrape every last bit. You want to say, well, okay, I can leave that because scraping that's going to take hours. Is it worth it? Sometimes it's not worth it. And so if you need a certain amount, you have to compensate for that loss. And so this is what this problem is doing here. Let's take a look at this problem. Solid sodium nitrate decomposes to solid sodium nitrite and oxygen gas upon heating. One set of reaction conditions gives a 95% yield. What mass of sodium nitrite will be produced by the decomposition of 1.50 grams of sodium nitrate? So first we need a balanced equation, so let's do that. Sodium nitrate, what's the formula for sodium nitrate? NaNO3, and then they're saying it's solid, and then they're going to heat this. So what we'll do is we'll add heat. When we add heat, then things can decompose. And, in this case, they tell us the decomposition products. They're going to produce oxygen gas and sodium nitrite. So sodium nitrite, what's the formula for sodium nitrite? NaNO2 and oxygen gas? O2. And we need to balance this. So to balance this, I'm going to need 3 oxygens on both sides. So I'll do this by 1/2, or just double these. So I'll just double this, and then I'll have 1O2. Make the gas. This turns out, this is going to be an aside topic, but this turns out to be a redox reaction. This is a redox reaction in which the oxidizer and the reducer are the same compound. And so, what's the oxidation state of sodium? Group 1 are always +1. Oxygen? -2. +1, -2. That means nitrogen's what? Nitrogen's variable, because nitrogen goes all the way from -3 to +5, so I'm going to figure out what it is. It is +5. In this case, nitrogen's +5. How about over here? Well, the same. Sodium's the same, +1. Oxygen's the same at -2, but nitrogen's changed to +3. And then oxygen over here is 0. You know, 0 times 2 is 0. It's just got to be. And so, you know, this is what happens. As you heat things up, you know, kinetic energy goes up and this kind of stuff. And as you heat things up, now, nitrogen, when you characterize, how would you characterize the nitrogen over here? Electron poor, electron rich, or neither really? Electron rich? Why? It can give 5 because it's got 5. Well, it's actually a +5. So +5 means it has extra electrons or it's missing some electrons. +5. No, well, +5 means it's missing electrons. So, like, for example, sodium. In order to go from sodium to sodium plus, does it gain an electron or does it lose an electron? It has to lose an electron. And so when we're going, and so in other words, in order to go from nitrogen 0 to nitrogen +5, it has to lose how many electrons? 5 electrons. It's got to lose those. So you got a +5, -5, those cancel out because it means 0. And so when we get positive charges, that means we lost electrons. When we have negative charges, that means we gain electrons. And so +5 means it's electron poor or electron rich? Electron poor. It's electron poor, and so it's going to want to take electrons. But you know, this is like, well, what can it take electrons from? It'd like to take electrons from some other species. So nitrate would like to oxidize something else. But, you know, and nitrate's pretty stable as is, but if you start heating things up, then what can happen is the nitrogen and the oxygen, well, who has the extra electrons that nitrogen might be able to take? Sodium? Not really, because sodium's already +1. It doesn't have any more electrons really to give up. However, oxygen is -2, which means oxygen has 2 electrons. But the problem is oxygen holds onto those electrons very tightly. Very tightly. But if you start heating things up, then things start to become more chaotic. Things start to become more violent. And you know what happens here? What happens here is that the nitrogen can attack the oxygen inside the nitrate ion. It doesn't attack all of them, it just attacks one of them. It attacks one of them and takes 2 electrons. So one of the 3 are lost, takes 2 electrons from it and creates oxygen. Here. You see that? And so this is a case where the oxidizing agent is the nitrogen in nitrate and the reducing agent is the oxygen in nitrate. The only way that's going to happen is if it gets very hot, you know, violent. Does that make sense? So this is a redox decomposition reaction. Nitrate, you should know nitrate is electron poor because nitrate is something you should know from this table. Oh shit, I just closed that table. Open that table again. Do you see nitrate on this table? Turns out nitrate is a strong oxidizer. It's here. Nitrate is a strong oxidizer. Although it's pretty bored down, it's still a pretty strong oxidizer. Here, nitrate. Strong oxidizer. Maybe I should show you how strong an oxidizer it is. Have you seen this? Read this. This is the. This one is. I think this one is it. Let's try this one. So you want me to mute this, or you're okay?
Oh my gosh, they're just outside.
Oops. Oh, you missed it there. Let me back up a little bit. This is more. Well, that first explosion was a small one. The second explosion was a big one. So I'm trying to show that was the footage I was looking for, the unedited version. They have an edited version on the news. Come on. All right. Yeah, I might have to. Do you want to see the rest of that footage, or?
Yeah.
Yeah. Yeah, you know what blew up was like an ammonium nitrate storage facility. That's, I guess that was the worst industrial accident in China. Do you know what the worst industrial accident in the U.S. was? No? Okay. I might as well show you that too. See, was I don't have the right video here. Yeah, the volume is pretty low. Let me try to bump up the volume.
Could it happen again? Could Texas City be another boom town in the worst possible way? 50 years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It feels very strange. I'm really glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it and it's real pretty to watch. And there were townspeople, about 100, lined the part of our parking lot that was nearest to the ship. They came down to watch the fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We get to see bits and pieces of paper bagging going up through the air and away. And my boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a grain ship. The grain is on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, a Monsanto secretary, was watching from her office window. And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster. The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off of the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City. This is Charles Hadlock. Texas City is trying to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around. Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives. The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as fast, as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
Or the lights just went out. I could not see more than 2 or 3 feet. And I thought, my God, it was a nitrate explosion. I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car which 2 people had been decapitated. Then I passed one of the 2 little planes that had been flying around overhead. Came down along the path that I took up to town.
I'm sure all of that glass came into us, and I must have gone like this, and so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it, and therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it moved me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, and it jarred, but nothing hit me.
Here comes another explosion. But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
We had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
So, like, redox reactions are quite a bit different than metathesis. When you make a precipitate or you effervesce gas or something like that, do you expect explosions to occur? Not like that, you know. In metathesis reactions, the charge doesn't change, the oxidation state. So you got sodium ions here, you have sodium ions there. Same thing with acid base. When you neutralize an acid base, sometimes you got to be careful because it could be a little bit violent, but it's not going to be nearly as violent as this. The difference in redox is that the charge on the element, on the atom changes, which changes how it behaves dramatically. And so something like sodium nitrate there, you know, well, nitrogen really wants electrons, and there's really no electron. Oxygen holds onto those electrons pretty tightly, so this is pretty stable unless it gets hot. If it gets hot, then it potentially could have a self reaction. That is an auto redox reaction. That is, it reacts with itself. However, in something like ammonium nitrate, now ammonium nitrate is very dangerous. You could see in China, that storage facility in China was filled with ammonium nitrate. The ships there were filled with ammonium nitrate. Well, what's so scary about ammonium nitrate? What's so scary about ammonium nitrate, take a look at the, it's not the oxygen. The oxygen and the hydrogen. What's hydrogen? Hydrogen is +1. Oxygen is -2. And oxygen tries to hold on to those electrons, so oxygen is not a great reducing agent. Nitrogen is +5. In nitrate, what is nitrogen and ammonia? Ammonium. Ammonium is NH4+. And so if hydrogen is +1, that means nitrogen must be -3. So this is +1, this is -3. So what's the difference? Well, one nitrogen has 8 more electrons than the other nitrogen, you know? And so you got two nitrogens. You got 2 nitrogens, one has 8 more electrons than the other. Are the 2 nitrogens going to be happy? Both nitrogens have 1 electrons. One has a deficit of 5 electrons, the other has an excess of 3. A total of 8 electrons. And so what you have is you have a good reducing agent and a good oxidizing agent in the same compound. Any compound, you know, most of the explosives are going to be like this. They're going to have a reducer and an oxidizer in the same thing. They're going to be unstable. there's a lot of potential energy here in ammonium nitrate. Whereas there's not so much here in sodium nitrate. Sodium nitrate we consider an oxidizer, and that's about it. So nitrates. Chemists are always very careful around nitrates. Like what he was saying, the chemist there was saying orange smoke. You saw that orange smoke. Do you remember the orange smoke? Nitrogen dioxide. The guy said it was sulfur. It's not sulfur. That's NO2. It's that characteristic orange smoke from nitrate. When nitrate oxidizes something, NO gas is formed. All right, that's some of the chemical properties of nitrate. Nitrates, one of the other ones, this is why there's a huge difference. HCl versus HNO3. Both are dangerous because both are strong acids. But one is especially dangerous. Why? Because, I would consider, you think, well, nitrates are unreactive in metathesis. Yeah, nitrates are unreactive in metathesis. Nitrates are unreactive in acid base, in the nitrate itself. But nitrates are highly reactive in redox. And so this is called what kind of acid? This acid you got to be very careful with compared to this acid. This is our standard mineral acid. H plus is the oxidizer. This is what we call an oxidizing acid. It's more dangerous in certain respects. So you got to be more careful around that kind of stuff. So be careful around nitrates. Have you heard of TNT?